Hey, welcome to the second video in the series for Rust 3D graphics in the browser. My name is Doug Milford from Lambda Valley. This video will be focusing on two-dimensional graphics and introduce you to some WebGL concepts. The previous video was about some boilerplate setup and WASM introduction, and the next video is going to be about 3D graphics. This gradient will be the result of this video. And this is what we're building towards as our final goal in the third video. As a reminder, I have the final project posted on GitHub at this location. Feel free to download or clone it for your own needs. I've commented out the rendering of the 2D portion that this video describes, but all the code is still there. You just need to call it within the main render in Rust. Let's get our hands dirty. Two-dimensional graphics! Let's begin by introducing you to some WebGL concepts. The first is that despite WebGL being used for three-dimensional graphics, it actually has no knowledge of 3D whatsoever. It's just taking basic instructions that you provide it and sprays color on the screen. The 3D is achieved purely through math, specifically relying heavily on linear algebra. Don't be scared if you don't have the best math skills. The math will pretty much be done for you, or at the very least you use a function that I provided and that contains the math and everything will work out fine. Someone so much smarter than myself has also figured out and pre-canned a lot of this math for you. All you need to do is know when and why you're applying their pre-canned math, and hence what I'm about to teach you in this video. Since WebGL doesn't know about three-dimensional graphics, how does it actually work then? Well, it thinks of your screen as a box. The x-axis goes from -1 to +1, and same with the y. They meet in the middle of your screen at point 0, 0. It doesn't matter how skinny or wide your drawing canvas is, it still just thinks of it as -1 to +1. It does have a z-axis that goes from -1 and +1 as well, and you can think of it as an arrow pointing at you from the center of the screen. So really, WebGL's universe is a cube where all axes go from -1 to 1. But the z-axis exists for a different reason than you might expect. It's not used for 3D perspective. For example, if I put a ball in the center of the screen of the WebGL universe, and I move it away from you on the z-axis, you might assume it would get smaller because it's getting further away. That's not how it works though. What it does is just use the z-value to know what should be drawn on top of what. If a pixel is behind something else, it simply won't perform the calculations. That's how it can gain enormous efficiencies in the 3D world. It's just bypassing calculations based on whether if something can be seen or not. That's it. End of story. Unfortunately, there's a twist. If you allow semi-transparencies, which I am, the z-value can no longer be used for efficiency. You have a pretty big performance hit on this, and you have to be careful to feed in your rendering instructions from furthest away to the closest. Well, if the z-axis isn't going to be automatically creating our 3D world for me, and I can't really utilize it for efficiency, is there even a point to the z-axis and z-values? Even though much of the benefit of the z-axis is lost when you allow semi-transparencies, you still need the z-values when you do your 3D calculations. The workflow begins where you provide some input data to WebGL. This could be positional data, perhaps some potential color data, maybe an image for coloring pixels, maybe even some data to calculate some special effects, or whatever you need really. Anything that will help you get your vision on the screen. You'll buffer the data, meaning provide the graphics processing unit, or GPU, direct fast access to that data. You have to provide two shaders. These are specialized mini programs that run directly on the GPU. One is called the vertex shader, and another one is called the Fragment shader, and they have very specific jobs. As a side note, your GPU doesn't know anything about 3D either, It's just really good at doing the math operations needed to perform the heavy calculations for graphics. Once the shaders are done with their job, the image gets transferred to the screen. Based on your positional data, triangles are created and will be the basis of how WebGL knows where to draw, even if you're drawing a round ball or something that has curves. Every computer animated film or computer game essentially works this way, and we'll be doing the same thing. Things look smooth only because the triangles are so small that you no longer recognize them as triangles. Triangles are the name of the game, which you'll see shortly. We'll use Rust to perform some pre-calculations and then buffer our data next to the GPU for this to work. WebGL will take your buffered data and pass it into the vertex shader. The vertex shader's job is to modify the position based on the fancy mathematics that I was talking about earlier. This is where the 3D can come into play. Based on your positional information, your camera position, your camera angle, the rotation angle of your object, and more, your data will be squeezed into the universe of WebGL from -1 to 1 on all axes. For 2 dimensions, the math is much more straightforward, which is why I'm doing it first here. Once the vertex shader is done doing the transformation for each position point, it'll pass that information down to the fragment shader. The fragment shader's job is to color the triangle's pixels. That's it. There can be many pixels per triangle, perhaps thousands. You can use a single color for the entire triangle, or you can use an image for the pixel information, which is how you can get images on your screen. Or you can even do your own calculations based on other inputs, which is how you can do some pretty cool effects. From there, the image that the fragment shader has drawn is transferred to the user's screen once it's all done. The entire process happens without the end user's knowledge. WebGL isn't actively drawing the triangles in front of the user in real time, it just swaps out the old image with the finalized new one once it's ready, which represents a single frame in our movie. So every time you render a screen with WebGL, you're really running a bunch of these mini programs on the GPU to morph position data and spray paint pixels onto the screen. In reality, you can have dozens or hundreds of different programs if you want all sorts of special effects. Again, I want to remind you about webglfundamentals.org. It's an awesome learning resource. It's not about Rust, but the WebGL concepts are there. I really can't do it justice here. Another fantastic resource is created by Mozilla. It's extremely thorough and very well written. I recommend you check both of these out. Let's get to some programming. I'll be picking up the exact place we left off in the previous video. In our Rust code, the first thing we'll need to do is connect up to our canvas so that we can draw it with Rust. So that it doesn't muddy up our main code, I'm going to create a new file called glsetup. I'm going to paste in some use statements that we'll need later. So let's create a function that will initialize and return back our graphics context. Before we get too far, I'll need to pull in this file into the lib and hook this function up from there. I'll call this from the constructor of Doug's client before I forget, because I will. And while I'm here, I'm going to set up my panic hook into the console so that we can get those messages when things go haywire. Okay, back to our function. These warnings and errors we're getting will go away once we fill this out. Let's get a reference to the window. And from there, let's get the HTML document. If you remember, in our index.html file, we gave the canvas an ID of Rust canvas. So we'll just use that as our ID when we are grabbing it from our document. To get the canvas in a form that Rust will be able to deal with, we need to do this funky line to dynamically put it into WebSys HTML canvas element. And finally, we can grab the graphics layer, which is the object we'll be drawing with. Yeah, that was pretty ugly. I have several unwrapped statements, which means I'll just assume everything's automatically going to work out of the box. If this were a real application, I'd actually do a better job of error handling. Be forgiving though, this is just a demo. Anyways, if you remember, in the index.js file, I grabbed the graphics context and enabled alpha blending as well as gave the blend function. Technically, in our canvas setup, we're grabbing the same graphics layer, so we can just do it from there. Since we've moved the graphic layer settings to Rust, I no longer need it here in the index.js file. Now that we have access to the graphics layer in Rust, I can also define other things. Let's set the clear color to black, meaning when it needs to erase everything, what color should it erase with? The four numbers being input stand for red, green, blue, and alpha, meaning transparency, with values ranging from 0 to 1 for each. We'll also set the clear depth, which can be between 0 and 1. Technically, you don't have to clear everything, but I typically do, so that's why I set it to 1. And now let's return our graphics layer to get rid of the error. Back in our lib file, we're calling our initialize statement, but we're not doing anything with it. Let's store it in our struct so that we have it long-term to use. Oops, looks like I forgot a namespace. And now let's store our graphics layer when we initialize Doug's client. Okay, so every time we call clear, it'll clear to black. I haven't set up the clear call yet in our lib file, so let's do that. This would be a good time to bring in the rendering context namespace as GL for short so they don't have to keep typing it out over and over again. And every time our render is called, we'll clear the screen with our defined color. Let's run this and see what we get. So we have our black screen. How do we know that what we set up is working? Well, let's change the clear color to be a greenish tint. If I change the second one to 0.5, which is the green value, our background turns green. Yep, the Rust code appears to be working. Yay! Later in the 3D portion, we'll be hooking up mouse events in this file. For now, I think we're done with it, so let's close this file. Because I know I'm going to have multiple programs, I'm going to set up some folder structures now. One is going to be called programs, meaning WebGL programs, and another is for shaders. Inside the shaders folder, I'm going to create two other folders, one for fragment shaders, and one for vertex shaders. The reason we separate shaders from programs is because a shader can be used in multiple programs. I might only have a couple of vertex shaders as the math for 2D or 3D transformations is pretty consistent across most, if not all, objects. But the fragment shader can do all sorts of special effects, so I might have a bunch of those depending on what I need. I'm actually going to begin with these shaders first and get them ready for us to use. So unfortunately, shaders are a mini program that are actually defined in a string. I wish it wasn't that way because the whole point of Rust is to create safety, and programming in a string is not safe. But usually it's okay. Okay, I'm lying. They're very brittle and extremely difficult to debug. But we march on. The syntax is similar to C. Since it's a mini program in its own right, it needs a main function. We'll be passing in some position data as an attribute, meaning the data we buffered representing our spatial coordinates. And also we'll provide a transformation matrix, which is a 4x4 matrix. This stretches and squeezes every one of our position vectors in the WebGL box universe. It's a uniform because it's the same exact matrix for every point. So you only have to pass it in once into the program and it's uniformly available. And this is where the heavy math comes into play. You ready? Okay, so that wasn't so tough. The 3D vertex shader will be a little more involved, but it's similar in concept. The GL position variable is the expected output of the vertex shader in WebGL, so that's why I'm assigning it here. So really this vertex shader is just doing a bit of linear algebra, which is what your GPU is super good at. For each point in your object, it'll take it in a vector with 4 values. It will then use the transformation matrix to calculate a resultant position. That will then be passed to your fragment shader, which will finalize everything by coloring pixels. This isn't the only way we could have done our 2D vertex shader. There are many ways, but to get you ready for 3D, I want to use this transformation technique of using linear algebra so you get used to the basic concept. Before I forget, I need to create a mod so that other folders can see this. Yes, this setup is currently over-engineered since we only have one file in here, but it'll get fleshed out soon enough. Okay, let's move on to the fragment shader. As a reminder, its job will be solely to color pixels. In here, I have to tell it what precision I want my float variables to be. High precision will be a higher quality, but it will hit your computer resources harder. I typically go with medium P or medium precision. The quality is still pretty darn good. Because this too is a mini program, it needs a main function. So every triangle that the vertex shader creates, it'll send down information about every pixel within that triangle and pass it down here. The fragment shader will color each pixel within that triangle on the screen. You can do all sorts of calculations based on the position of the pixel within the triangle, or some color based on some uniforms passed in, or whatever. Often you'll see someone do an example of a gradient triangle to illustrate. We'll be doing a gradient rectangle further down in this video. The two-dimensional drawing I currently want to draw will be one color. So I'm going to provide it with a uniform called U color. The U stands for uniform. For kicks and giggles, I'm also going to send down an opacity uniform. The reason being is that for everything that I draw, I want to have the capability to fade it in and out of existence smoothly. For those of you squirming in your chair because I can technically set the alpha on our colors instead of passing a separate uniform, relax. Part of why I'm doing this is to prep you for how I'm going to be doing 3D. Anyways, from there it's just a simple matter of returning a vector 4 with the correct color for that pixel. I'm going to just take the red, green, and blue values directly from our uniform and then multiply the colors alpha against our opacity uniform. It doesn't have to be this simplistic, it just fits my current needs. So you know, GL frag color is a built-in variable in WebGL, and that's how it knows what your final color is. If you don't allow semi-transparent objects, then WebGL can be much more efficient. WebGL just checks which pixel is in front, and if a pixel is already in front, it doesn't even bother with new calculations for the new pixel. That's why the default is that the blending is not enabled, because there's a pretty big performance hit for semi-transparent alpha blending. But for what I like to do, it's pretty needed for quality purposes. Let's close that up. And before I forget, let's create our mod for the fragment shaders so that other folders can see it. We need to tie both our fragment mod and vertex mod into the shader mod. And to go all the way up the food chain, let's establish our shaders mod in the lib file. Let's now create our WebGL program. And to be proactive, I'll create my mod. And to be good citizens, I'll bring it up into our lib file. Back in our program file, I'll bring in some namespaces that I know I'll need. I'm going to create a struct. This is going to encase our program definition and buffers. Yeah, I know the word program is being abused all over the place here. Hopefully it's not too confusing. The program I'm referring to here is defined as a WebGL program. It's the combination of our shader programs with some data buffer information. To set that up, we need to bind the shaders together so that when this program runs, it knows that that's the pipeline, so to speak. Let's create an implementation block for color 2D and create the new constructor. Because the process is so standard in creating programs, I'm going to create a common functions area and have the code in there. I'll come back to this once I'm done. I'll create a file called common funcs. I'll bring in some statements that I know I'm going to need. And if you remember, our shaders are just strings. Well, they have to be compiled at runtime, so I'm going to write the code that does that. I'll need the graphics layer reference, what the shader type is, meaning if it's a vertex shader or a fragment shader, as well as the source code of our shader that we put into that string. The result will be a compiled WebGL shader. We tell WebGL to create a shader, meaning reserve a spot in memory for our compiled shader to live. I'll handle the error if it has an issue doing so. So this is like a pointer. When we perform our operations with the graphics layer, we'll need to provide that so that it knows what it'll be working with. I set the shader source, meaning associate the code we wrote in the string with this shader pointer, and then I tell it to compile. Let's check if everything worked okay by verifying the compile status. We'll assume false if it can't read the compile status. If it's okay, we'll just return the shader reference. Let me put the initial bracket on its own line so that the if statement doesn't bleed into its body. If it can't compile, let's return an error with some information. So that's the same process for compiling shaders, whether it's for a fragment shader or a vertex shader, 2D or 3D or whatever D you're doing. That's why I put it in a central spot so I don't have to write the code over and over again. In line with that, the code to link the shaders to a program is the same no matter what. So I'll create a function to do that. The parameters I'll need are the graphics layer reference, the vertex shader source code, and the fragment shader source code. We'll need to tell WebGL to create a location in memory for our program. Again, this is like a pointer, and I'll handle the error if something goes wrong. I'll use our newly created compile shader function to create our vertex shader. First, I pass in our graphics layer reference. At the top of this file, I pulled in the use statement and gave it an alias of GL so I didn't have to type it over and over again. From there, we have access to some constants, and to tell WebGL what type of shader it is, we just use the vertex shader constant. Lastly, I'll pass in our vertex shader source code. We'll call unwrap at the end. Really, if this has an error while creating the shaders, then we'll see a red message in our console. Let's do the same for our fragment. And from there, it's a matter of attaching our shaders to our program and then linking it. Just like we did with compiling shaders, let's verify that the program was successful in linking the shaders to the program. Bear with me for a second. Okay, that should be sufficient. Now we have centralized code that can compile a program with its shaders for us. Let's make sure it's available to our entire code. Okay, first, let's bring in the common funcs namespace into our Color2D program with an alias of CF. Whoops, seems I have an error in my common funcs. I forgot an ending bracket on my results. And now I guess I forgot my use statement. Man, 2 in a row. Brutal. To use our new function, we can just call it and pass in our graphics layer along with our source code for the shaders. And now we can fulfill creating our new Color2D struct. If you remember, our shaders were expecting some data. Specifically, our vertex shader is expecting position data and some transformation matrix. And our fragment shader was expecting a color information as well as opacity for the entire object. Let's set each of those up one by one. The first is our position information. We're going to feed in a rectangle, but WebGL only understands triangles. So this is actually going to be represented by 2 triangles. And the way you do this is you give it the coordinates in a counterclockwise fashion. So I'll create an array that has the following vertices: 1, 2, 3, 4, 5, 6. So you may have noticed we counted 2 of the vertices twice. There are multiple ways to be more efficient, which we'll actually do for our 3D program. I'm doing it the inefficient way for the Color2D program because I want you to see multiple ways of doing the same thing, but also because it's easier to understand this way at first. We're just going to draw the raw array of vertices, and then when you're more comfortable with WebGL concepts, we'll ramp it up to be more efficient. So why is it important to go counterclockwise? WebGL tries to be efficient whenever it can. If you disallow semi-transparencies, WebGL can figure out if something is facing towards you or not based on whether it sees it going clockwise or counterclockwise. If the triangle is turned around, which it'll see as a clockwise orientation, it knows it never has to draw it because your eye can never see it. The concept is called face culling. So when a 3D object spins around, WebGL will easily know what it has to draw and what it doesn't have to bother with. It tries to be efficient whenever it can. Now, if you have semi-transparencies enabled, then all bets are off. There's a chance you can see something even if it's not facing you. That's why we had to enable blending earlier in this video. But that means I take a serious hit on resources because it has to do a ton more calculations. That's your choice as a developer. I'll create an array to hold our rectangle vertices. I'm using F32s because that's the precision I'm using in our shaders. F64s are probably not going to improve things very much. I'm going to start at the top left hand corner where X is 0 and Y is 1. It really doesn't matter where you start. It's more important that you just go counterclockwise. So my second vertex is at 0, 0 and my third is at 1, 1. That completes one triangle. To do the other, we specify the top right hand corner again. Again, it's fairly arbitrary where to start. Let's go back to the bottom left and to the bottom right, and that completes our counterclockwise triangle. Cool. Now we have 2 triangles, both facing forward to create a square or a rectangle. Even though this is a super simple example, every piece of computer-generated graphics is based on little triangles like this. Whether it's a square or a complex model of a gargoyle, it's all just tiny triangles. We need a way to get this information to WebGL in the GPU. The way we're going to do this is by what's called a buffer, meaning creating a memory location with WebGL extremely close to the GPU so that I can grab it and utilize that data very quickly and efficiently. Let's create a temporary memory buffer. We'll also get a pointer to our vertice array. We're going to convert our array into a JavaScript form like so. We provide the memory buffer and then give it our vertices location as well as the end location, which is just the start point plus the length. Let's create a final buffer that will hold this converted array. And now we have to tell WebGL to use this buffer that we're about to fill. We do that by saying gl.bindBuffer. Tell it it's an array buffer type, and then give it the buffer pointer we want to bind to. And now WebGL is bound to that buffer, meaning pointing to it and ready to do whatever commands you want to it. So let's shove our array information into it. Again, this puts our data extremely close to the GPU so that it's easy and very efficient for the GPU to access it. I'm making it a static draw, meaning I don't believe our buffer will ever need to change, and I want to stick around for as many renders as I like. If you are planning on updating your buffer frequently, perhaps every render, then you should probably use what's called a dynamic draw. There's also a stream draw, meaning you're planning on using it once and only once. WebGL will be more efficient if you specify what you plan to do with this buffer, which is why we do that. Okay, so when we need to use that buffer on the render, we'll need to access it. So let's create a field on our struct so that we have access to it later on. And now during initialization, I can assign it like this. Okay, that was a ton. If your head isn't spinning by now, you're not human. What we just set up is only the position data being passed to the vertex shader. The other input data is going to be much easier, so don't despair. There are currently several files that have warnings on them. That's because technically they're unreachable code. I'm tired of looking at those warnings, so I'm going to wire our WebGL program up in our Doug's client. Since I need a GL as a reference, I need to make sure GL ownership transfer happens afterwards. Okay, let's close some of these. We still have our uniforms we need to set up, such as our transform uniform. For the uniforms, I'll create fields on color2D for each. We have our uColor, meaning uniform variable holding our color data. Our uOpacity, meaning our uniform variable holding our opacity information. And our uTransform, meaning our uniform transformation matrix. And those are almost trivial to set up. We just ask where the location is from WebGL for our program. I actually need to put program at the bottom because each of the uniform declarations are borrowing it. If I had it at the top, the ownership gets transferred before I can use it. Now let's set up each of our uniforms. Bear with me for a second. There's just one more field I want to add, and that's the vertice array length. We'll need that in the render, and I won't have access to that array anymore at that point. So I'll just store it here for later use. Okay, so now I have the buffers and locations for all my inputs into the shaders. Now, on render, it's just a matter of filling in the necessary data. The position data won't change and is already primed and ready to go near the GPU. I'll need the information from the struct itself, so I'll pass in the self variable. I'll also need the graphics layer reference, so let's bring that into, and now I'm going to have the color define our bottom, top, left, and right so that they have control of where the rectangle will be positioned. Lastly, I'll need to know the canvas dimensions to correctly create our transformation matrix. Is this the right way? Passing in this information and then creating uniforms instead of buffering? There's no right or wrong way. Depending on what you're trying to accomplish, there are better and worse ways, but that's the benefit of WebGL or any low graphics API. It gives you the flexibility to set things up based on what you need. If you need efficiency in your program, you might set it up differently than if you needed flexibility. That's why so many pre-canned abstractions fail to achieve sufficient efficiency or flexibility, because they can't predict what you need and why, so they have a hard time optimizing based on your specific needs. Anyways, I'm sidetracking. If I don't hook this up in our lib, we'll see this warning for the entire time, so I'm going to go ahead and do that. I'm going to hardcode some values at first just to get something on the screen. I'll tell it to fill the entire screen. Remember, WebGL thinks the axis goes from -1 to +1, but I'll create a faux screen dimension of 0 to 10 for example purposes. Let's put some comments on each of these so it's a little clearer what they represent. Okay, back to our color 2D program. The first thing we're going to do in our render is tell WebGL we're about to use our program that we created. As a reminder, we set up our position vertices as a vec4, meaning a variable with 4 floats, so that the linear algebra math is easier. But our data only has an x and a y. If your destination attribute is bigger than your input, it will just fill it in with zeros for the rest, which works for our situation. Now we inform WebGL that we want to use the buffer data that we did in our initialize. We're going to assign it to our initial attribute, meaning our position attribute. You can actually pass in multiple attributes. We won't have one in the Color 2D program, but we'll do multiple attributes in the gradient example we'll do shortly. The next parameters indicate the size, meaning how many data elements there are per vertex attribute or position. We have an x and a y, so ours is 2. If we were doing x, y, and z, this would be 3. You can get as many as 4. After that, you have to create a new attribute. As I explained recently, we're putting each vertex into a vec4 even though the size is only 2. Zeros will be placed in the remaining spots. I'll tell it to expect floats. The next is if we want our values to be normalized, which I don't. And the last two are regarding stride and offset. These are used if you have an array that holds various data, not just straight vertices. We're just doing straight vertice data, so both are zeros. And now we just tell WebGL we're all good to go on the attributes by enabling it. Uniforms are going to be easier. As a reminder, uniforms are available to both the vertex and fragment shaders. As opposed to attributes, which the vertex shader can modify before passing to the fragment shader, uniforms are the same throughout the pipeline and available to both the vertex and fragment shaders if you need them. So let's hardcode our color. I'm going to give it no red, half green, and half blue, and make it completely opaque by giving it an alpha of 1. What we should see is a teal colored rectangle. I'm using a uniform 4 because our shader is expecting a vector with 4 entries in it, specifically 4 floats. For our transform uniform, I'm going to need a little bit of math. This is where some linear algebra comes into play. I'm going to create it in my common funcs area. I'm going to need 2 different functions and then we'll combine them together in a single matrice. The first is going to be a translation matrix, meaning moving our object around in space. I'll accept an x-axis shift and a y-axis shift, and also a z-axis shift. Since we're doing 2 dimensions at the moment, we'll be putting a 0 in for the z. But because the z is a parameter, we'll be able to reuse this exact function for the 3D world if needed. We'll need 16 spots to handle the 4x4 matrix. So the first 4 values stand for the first row, the second 4 values stand for the second, and so on. That's how you can get away with one-dimensional arrays pretending to be a 4x4 matrix. I'll create a mutable return var array of floats defaulted to zeros. I'll first make it our identity matrix by putting 1s on the diagonal. And then from the bottom row, I can put in our transform for each axis. You might be wondering why we're doing it this way. Well, for 2-dimensional transformations, it's not hard to do the math manually. You can even do it in the vertex shader. However, as you get more dimensions, and as you're doing more transforms such as rotating and scaling, doing it by hand becomes extremely tedious and error-prone. I'd rather set up a few basic matrices and let the computer take it from there. Call me lazy. Now I want to create another function to scale my rectangle. That way we have it as big or small as we like. It's going to be even easier than the translation matrix. We just have the caller define the scale in the x, y, and z directions. From there, we can create our return var like we did before. And instead of initializing the identity matrix, we just put our scaling values in for the diagonal, and that's it. Back in our 2D program, we can now call our translation function to get that ready. We're scaling our dimensions to be between -1 and +1, which is the only coordinates WebGL understands. Since it goes from -1 to +1, the actual range in the x-axis is actually a size of 2. So that's where our 2 comes from. We divide the left by the canvas width so we can get a percentage of how far over it is, and then subtract 1 to adjust for the fact that it starts from -1, not 0. We do something similar for while. For z, we don't need anything because this is a 2-dimensional transform. We do something similar for our scaling. This time we're only concerned about size, not position. And now we just need to multiply these 2 matrices together to get our final transform. I searched for a built-in way to multiply 2 matrices, but I couldn't find one, so I built my own. It's pretty raw, but it should work fine. I'm just going to paste it into the common funcs area as I don't want to bore you with the math. It's just basic linear algebra multiplication. And now I can get my final transformation matrix. This is now a matrix that incorporates both our translations, meaning moving up, down, left, right, along with our scaling, meaning make bigger or smaller. Was this necessary to create a translation matrix and a scaling matrix and then combine it into a final transform matrix? Absolutely not. The math is so straightforward with 2 dimensions that it would have been easy to do manually, but I'm trying to coax us into thinking in terms of linear algebra. The math gets really hairy in 3 dimensions or more if you don't use linear algebra. Now that we have that, we just need to tell WebGL what the matrix is for the uniform. Oops, I guess I forgot the opacity information. Since you didn't tell me, that's on you. Your fault. Every piece of data is primed and ready to go. The last thing to do is call the draw arrays in WebGL. We're going to tell it to assume triangles. This has multiple options which I'm not going to get into. We tell it where the first element is in our array, which is typically 0, and then we tell it how many indices to expect, which is the length of our array divided by how many data pieces per vertex. Since we only have an x and a y for our 2D example, this would be 2. Okay, in theory, this program is done. We're ready to run this now and see what we get. We get the entire browser in the yummy green blue. Let's play around a bit. We told it that the browser height and width are both the size of 10, which is obviously wrong. Our browser isn't a square at the moment, but it's really arbitrary at this point. It doesn't really matter that in fact it's not 10. What matters is that we said it starts from 0 and goes to 10, and our width is 10. The scaling function we created will translate everything from -1 to 1 anyways. Hey boss, if you tell me the browser height and width are 10, that's cool. I'm just gonna stretch it until it fits anyways. That's probably the worst impression. Anyways, if I change the height to 20, now our top, which we said was 10, is only half the size of what we told it the canvas height was. And when we change the canvas width to be 30, our box will only cover a third of the width of the browser. So really, things are being stretched and squished. But I want my dimensions to be maintained regardless of the size of the browser. To get accurately sized drawings, we're going to need to know the actual canvas height and width. I'm going to create a new file to hold some application state. I'm going to bring in a couple of namespaces I'll need. In here, I'll create a struct representing the state of the application. I'll add fields for the canvas height and width. And while I'm at it, I'm going to add one for the current time as well. You may be wondering why I'm actually storing these, since really they're available in the update itself. Well, I've had the pleasure of creating my own layout system so that I don't have to use HTML or CSS. It's built entirely in Rust. As such, the canvas height and width is important for calculations of the placements of all my UI elements, and hence needs to be available in more places than just the update and render. We could do without it for this entire video, but this is just how I like to structure things. You may be wondering why I'm not storing it in Doug's client. After all, we're storing other data in there, like our color program. Well, I like to keep only WebGL specific things in Doug's client. The color program is specific to WebGL, but I use the canvas height and width in more places than just WebGL. So it's not specific to WebGL, even though it's used there. I like to include in the application state so that I always have it handy. And we'll be expanding on this as we go to include more data. Anyways, you can decide for yourself if I'm whacked or not. Let's implement the new constructor and default everything to 0. With that, we can create a shared version of our data with our package lazy static. The mutex creates a lock around our data, meaning that one and only one thing can be accessing it at a time. I'm also using arc, which allows multiple references to our data, so you can easily and safely send data down multiple processes. Often you'll see the arc mutex pattern, but not the mutex arc like the one I've done here. I did that on purpose, and it's not a mistake. The purpose of the arc mutex pattern is to have something that's accessible and mutable for multiple references. That's not what I'm trying to do though. I'm trying to have many read-only copies of my data to perform any derivable calculations from that as the source. But updates should never actually mutate, only replace the state from the next reader. So in essence, I have multiple versions of immutable data. There are some advantages to this similar to how Redux works, but this is not something I want to sidetrack on for this discussion. If you are lost during this section, don't worry about it. Anyways, I'll create a procedure that will update our data. We'll pass in the time, canvas height, and canvas width. First, I need to get a reference to my data, so I lock the mutex and unwrap it. Then I'm going to replace my arc with a whole new arc. I'm not mutating data, mind you. If any process has to access the previous state, they would have no knowledge that this is happening, nor should they. This prevents race conditions and other concurrency issues. At the end, I'll clone the remaining fields. If you're familiar with Redux, think of this as a little reducer. You can make a good argument that there's no reason for us to be storing the canvas size every update, and that's a good point. There are more efficient ways of doing it. But if I don't draw the line somewhere, this will be a 4-hour video by the time we're done, and I'll have gone insane. Now that we have that, I'll create a function that will get the application's current state whenever we need it. Let's add app state to our lib file. Oh, I guess I forgot to include lazy static. Whoops! Let's do that right now. In the update, let's update our application state. And in our render, now we can get our state and use the canvas size for more accurate drawing. Let's run this and see what we get. If you see in the bottom left-hand corner, there's a tiny square. Well, 10 pixels is actually really small, so let's make it a little bigger. I'll make it 100. As you can see, as I resize the browser, our square remains a square and the same size. Now, there is some jittering going on. That's happening because there's a slight lag between the HTML canvas's size and when I pick up that signal. However, I doubt people are going to be resizing their browser like this very often, so I'm not too worried. So now we have a way to consistently size our objects. But having something hang around the bottom left-hand corner isn't really what I want. I want to have it centered on the screen, remain a square, but adjust its size to fill up the height and width as best it can. To do that, I'm going to add some fields to our app state. I'll add something for the bottom, top, left, and right. I'll default each one of those to 0. And let's do some quick calculations. To make sure our square is as big as it can be without cutting off, I need to find the minimum height or width. I'm actually going to make it slightly smaller than that by multiplying by 0.9 so that we can see a little extra space between our square and the edge. To calculate the control variables, I need to know half the display size, half the canvas height, and half the canvas width. From there, the math is pretty easy. Bear with me while I bang this out real quick. And now we're ready to use it for our render. Let's just replace this hard coding. I could have done the calculations in the render. However, that bleeds logic into that area that should focus solely on rendering. If it's doing calculations in this area, it probably needs to be refactored elsewhere. Okay, let's see how that looks. So now I can resize the browser and our square will always be in the center and fill up the smaller of the height or width. We did leave just a bit of room so that it wasn't butting up right against the edge. Okay, so that's just a single color. Often tutorials will do a triangle or a rectangle that has a colorful gradient. Let's do that. It will give me a chance to show you how to add multiple attributes to a program. I'm going to start by copying our vertex shader so that we can make some changes. And I'll add it to our mod. Now we're seeing a warning because the shader isn't being used anywhere yet. Pretty soon. I'm also going to copy our fragment shader so that we can make some changes once we're ready. I'll add that to our mod. And let's also make a new program using our color 2D as our template. And add that to our program mod. In the program itself, I'll change the struct name to color2D gradient. I'll use our new shaders. And to show you what program I'm hitting, I'll give it a reddish color for now. Okay, so we're getting all sorts of warnings because we're not using this program yet. Let's add it to Doug's client to get rid of those warnings and then use it whenever we like. I'll initialize it in our constructor. And now let's use it in our render. I'll make it slightly smaller than our other square. So really we should expect to see a reddish square with a teal border. And there we go. With the Color 2D program, we're storing our data inefficiently. So I want to take a moment to make the new program more efficient before we actually make it a gradient. If you notice, we're storing our vertices multiple times. I'm going to remove our redundant vertices. Oops, I forgot to change the dimensions of the array. So now this only represents 4 vertices, which you would expect for a rectangle. We're using zero-based numbering as that's what's often used in programming. With that information, we can now identify individual triangles by using the indexes. Remember, it doesn't matter how we create our triangles based on the 4 vertices. What matters is we create them in a counterclockwise fashion. So one way of doing that is going from 0, 1, 2, 2, 1, 3. So is this really more efficient? Didn't we get rid of 4 values but instead added 6? In a simple two-dimensional rectangle, that may be the case. But when the object you're representing becomes much more complex, perhaps representing thousands of three-dimensional vertices, many of those touching several triangles, having redundant data starts to become inefficient and far more prone to error. If you had to update a single vertex, you'd have to remember to do it in multiple places. Let's buffer that data similar to how we did the vertice information. I'll create the memory buffer get the indices location, get the JavaScript representation of that, create the actual buffer, bind it so that it knows what buffer to shove the data into, and then actually shove the data in. Notice that I'm using an element array buffer. That's how WebGL knows that this represents the index array and how it should combine that with our vertex information. I don't expect these indices to ever change, so I'm making it a static draw for efficiency purposes. I'll need to store the index count to use that during our render. I could hard-code it, but if I use this program as a starting point for some other program, I'd have to remember to change that hard-coding. Instead, I'll just store it in the struct, and then set it in the constructor. To be able to use my indices like that, I can't use the draw arrays in the render. Instead, I'm going to use draw elements, which assumes I've provided index information. And now the compiler is telling me that I don't need the rectangle vertex array length anymore, so let's just delete that. Let's run that and verify we see the same image. Yep, we're good. The indices are decoupled from the vertices to an extent. The vertices define your object, but the indices are really the driver of what gets drawn. But I promised a gradient, so let's proceed with that. I'm not going to be passing in a color uniform, so I'll get rid of that. I'll create a new buffer for our colors. This will be used as an attribute similar to how we did vertices. I'll create the buffer, but I'm not going to fill it in our constructor because I want to allow this one to be filled dynamically, meaning it can be a different color on every render. So this section is where we activate our vertices every render. Let's do something similar for colors. We'll bind the color buffer. We'll tell it that the vertex shader should expect to use index 1. The vertex buffer is the first one and has index 0, so this would just be the next one, index 1. We'll pass in the 4 values per vertex, specifically our red, green, blue, and alpha values for each vertex. And the rest is just the same. And we'll also need to enable it. In our vertex shader, we need to add the attribute. Since this is the second attribute, it will really correspond to our index of 1 we just set. Now, attributes can only be used in the vertex shader, but there's nothing stopping us from transferring that data down to the fragment shader. To do this, we create a varying variable. This is how we can transfer custom data in the vertex shader to the fragment. I'm using a low P, meaning low precision, because color data doesn't have to be very precise. And let's just assign it. In the fragment shader, if we declare the same varying variable, our data will populate appropriately for the pixel it's trying to render. If the pixel is somewhere in the middle of the triangle being rendered, it will average the color based on each color of the vertices. That's how our gradient works. And if you can visualize how that process happens, you'll have a much deeper understanding of how WebGL works under the hood. And now let's use our new color as the basis of our output color. I'm still using the opacity, which we'll play with shortly. Okay, back to the code. Our shaders are ready, but we haven't really provided any color data. Let's create an array. We've defined that we'll be passing in the 4 values for every vertex, so we'll need 4 values for 4 vertices. So we create an array of 16 F32s. Each row will have a red, green, blue, and alpha value, in that order. The first vertex will be red, and the second one I'll make green. The third, I guess I'll make blue. And last one, I guess I'll make white. Each of the alphas have 1, meaning they're fully opaque. We're going to prep this data like we've done before. This time though, I'll be using a dynamic draw instead of a static draw. It's true that since I'm hard coding this stuff, it really should be a static draw, but the purpose of this exercise is to demonstrate how to do a dynamic draw, which we'll do for a 3D sine wave. Normally, if colors will change at all, you'd pass them into the render function. I'm too lazy to do that right now though. Bear with me for a second. Notice that we're able to buffer this data because I'm still hooked up to the original color buffer. We didn't bind it to any other buffer yet, so we're still pointing to that buffer. Let's run it and see what we get. Ooh, that's nice. And you can play around with the colors if you like, even the alphas. If I remove the red and green alphas, the white and the blue will fade into the teal background. And now I can use the opacity input to adjust the entire object if I like. Now it's much more subtle gradient because now it's semi-transparent. Okay, let's clean up a bit for the next section. As a reminder, much of what I did in the 2D section was to prep you for what we'll be doing in 3D. So really, a lot of the learning is done. We'll just need to take it the last mile and add some bells and whistles. To refresh your memory, this is what we'll be building in the next video. Exciting, huh? I know this video was quite lengthy and you're a trooper for getting through the entire thing. But it's going to be well worth it once we get to 3 dimensions. Thank you very much for watching this video. My name is Doug Milford from Lambda Valley, and I look forward to seeing you next time.